Good morning, everybody. And today we're going to continue with the concept of the limit. Let me remind you what we already did. So after calculating some things using the definition and seeing some examples of functions that don't have limits at certain points, then we started to gather up some theorems, some tools to work with when we don't want to always resort back to the definition. And what we already did was arithmetic of limits and several small theorems that relate limits of one function to another. So for example, if f is greater than or equal to g, and both have limits, then the limit of f is greater than or equal to the limit of g. Remember we did that? And some theorems of that family. So what we're going to do today is continue gathering some tools like this. And the first one is a very, very, very useful theorem. And it has a name, it's called the Sandwich Theorem. And it says the following. Suppose that for any x in a neighborhood of A, this time we're going to have three functions, and they satisfy that f of x is between h of x and g of x. For any x in a certain neighborhood of the point A which we're interested in. Also, assume that the two outer functions have limits at A. That the limit of h of x as x approaches A equals L, and g has the same limit. So this also equals the limit of g of x as x approaches A. So these are the assumptions of the theorem. And the statement is, then the limit of f of x as x approaches A also exists and is also this L. I want to first make a little sketch to convince you that this is true. Then I want to prove it formally using the definition of the limit. And in particular, I want to tell you why it's called the Sandwich Theorem. Okay? So the sketch is something like this. We have let's say that this is the point A. We have a function g. Here it is, something like this. So let's say this is g. And we have a function h. I'm going to draw h in blue. And the only thing I have to guarantee is that h is always underneath g, right? And that the limit of h at the point A is the same as the limit of g. So the drawing of h maybe would look something like this. So this is going to be h. Do you agree that this is the picture that I should expect for g and for h, right? And now what I'm told is that there is a third function, f. F is trapped between g and h, so it cannot leave this in-between region. So let me draw it in orange, something like this and something like this. And do you agree from the drawing that intuitively it seems convincing that f doesn't have much of a choice? F is also going to have a limit at A, and that's going to be the same value as the limits of g and h. It has to somehow squeeze through this value here. Do you see that? Does everybody agree? So that's the picture and that's the intuition. That's not a formal proof. Okay? So let's write a formal proof. And for the formal proof, I'm going to have to resort to the definition of the limit. Okay? So proof of the Sandwich Theorem. How do I start? Good. Let epsilon be greater than 0. What do I know and what do I need to show? I know that H and G have limits and that those limits are L. I need to show that F has that limit and that that limit is also L, right? So the key to proving this is, remember let me this is going to be scrapboard. What I know is that there is a neighborhood in which G satisfies G of x minus L is less than epsilon. This is the statement that G goes to L, right? It's just part of it. There exists a delta such that if x minus a is less than delta, blah, 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 then this holds. Do you agree? Everybody? This is the same as writing. This is the same as writing, and that you should already feel comfortable with, that G of x is between what and what? Right. L plus epsilon and L minus epsilon. This statement is saying that the distance between G and L is less than epsilon, which is the same as saying that G is confined to being between L plus epsilon and L minus epsilon. Does everybody agree that these two statements are the same? So this we know. This is the we know part. Similarly for for H. H satisfies this. And therefore, H satisfies, again, I'm going to write it in blue, do you agree? Now, what do I want to show? I want to show that F satisfies this, right? Therefore, I want to show that F satisfies a statement like this in blue. Do you agree? Because they're the same thing. And if you notice that, then the proof suddenly becomes very easy. So leave a line here for the arguments that precede the statement. But the statement is going to be f of x is less than or equal to g of x. This is known from the data, from the assumptions. And g of x is less than L plus epsilon. That's from here. Do you agree? Similarly, f is greater than or equal to h of x. These are the assumptions. And h of x is greater than L minus epsilon. And taken together, there we have it. F is between L plus epsilon and L minus epsilon. And therefore, F minus L in absolute value is less than epsilon. Do you agree? Does everybody see? This is a very simple proof. As long as you note this, that these two statements are the same. We've been saying that like a million times. We're going to say it about a million more. But still, it's very important to note that. I know that some people have this kind of a barrier that they find hard to cross of seeing this and remembering it's the same as this and moving freely between the two. Okay? So now we have to formalize the details. So take delta to be the minimum between delta 1 and delta 2, where delta 1 guarantees this in the definition of the limit for G, and delta 2 guarantees this in the definition of the limit for H. So let's write that, where delta 1 implies, let me write this a bit informally. Okay, I can add the details. So where, maybe I will write it formally. You know what? Let's be very formal. Where x minus a is greater than 0, less than delta 1, implies g of x minus L is less than epsilon, and x minus a is less than delta 2 greater than 0 implies h of x minus L is less than epsilon. So these delta 1 and delta 2 exist. That's precisely the statement that the limit of g is L and the limit of h is L. And if I take delta to be the minimum of the two, then I know that x, which is, okay, so let's add one more line. Then, if x minus a is less than delta, if it's less than delta, it's less than both delta 1 and delta 2, because delta is the minimum. So this holds, and this holds. Therefore, the statements that we wrote in blue hold. So if x is blah, 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 then this holds, and that completes the proof. Okay? As always, the way I think is to start from the end, is to start by how do I show this? And then I gather up the deltas which guarantee it, and I add them up after they reveal themselves, after they show up somehow in the calculation. Yes, question?
I didn't understand how you write that line from those blue things.
Do you agree that this is the same as saying, this in particular guarantees just this? So I wrote this.
No, but like, why fx is in the middle of h and g?
So why is fx between h of x and g of x? That's the assumption of the theorem. Look back at the theorem over on this board. That's what we're assuming. Okay? Suppose that this holds. Otherwise, it would, of course, wouldn't be true, and otherwise this whole picture wouldn't be relevant to anything. Just by taking three functions that two have the same limit doesn't imply the third. Okay, this is exactly the... Oh, and I wanted to tell you why is it called the Sandwich Theorem. So what you should imagine is two slices of bread, G and H being the slices of bread, and F being the jelly or whatever you prefer putting in a sandwich in between. Okay? And this is one-dimensional, so you're just seeing a cross-section of the slices of bread. Maybe you should think of something more Israeli, like a pita, you know, which is kind of wigglier. But when you do, this theorem has an analog in higher dimensions. And for example, in 2 dimensions, you'd really have a function in 2 dimensions and a function in 2 dimensions and cheese in between. Okay? So that's the Sandwich Theorem. So this completes the proof. Let's add our little Helmosh here. And let's do a quick example. Suppose we want to calculate the limit as x goes to 0, let's say. Let's take it to 0. Oh, we didn't define one-sided derivatives yet. Okay, let's postpone this example. I want to do a few more things and then we'll get to this example, okay? Let's postpone it just a bit. Okay, so the next theorem that I want to prove, so this is a tool. We're going to see an example. We're going to see several examples in a minute. But I want to do some preliminary things first. So I want to first write another theorem. And the next theorem says the following. Okay. If f is a function that satisfies that the limit as x goes to a of f of x is 0, and g is another function which I don't know anything about its limit. The limit may even not exist, but it satisfies that it's a bounded function, and g of x is bounded in a neighborhood of A. So I'm taking two functions. One has a limit and it's 0. The other one is just bounded. Then, and the statement of the theorem is, the limit, as x goes to A, of f of x times g of x is also 0. Okay, the limit of the product is also 0. If g had a limit, L, whatever that limit were, this statement would be trivial from arithmetics. Do you agree? If f goes to 0, if f goes to 0 and g goes to L, then the product goes to 0 times L, which is 0. Do you agree? So the reason for this theorem to say something beyond arithmetics is that here I'm not assuming at all that g has a limit. In particular, it can not have a limit. Okay? So I want to prove this theorem. And so all the proofs we did so far stemmed from the definition of the limit. We always went back to that definition, and all the proofs we didn't do so far also stemmed from that definition. So we didn't prove everything, right? But even the things we didn't prove, you have to go back to that definition of the limit. As we accumulate theorems, we don't always have to resort back to the definition. For example, the way I'm going to prove this theorem is by using a theorem that we already proved. And that's okay. Once you know a theorem is true, you can use it. You can rely on it. Okay? So I'm going to prove it without going back to the definition of the limit. Okay? Ready? Okay. So, we know that g of x in absolute value is less than some m in a neighborhood of A. Remember, this was the definition of being bounded. Remember that? Or it was an equivalent definition. Another way of writing it is that g of x is between some big M and little m. Remember that? Everybody? Okay, so this is the boundedness of g in a neighborhood of A.
Should be or equal to.
Doesn't matter. It's an upper bound. You can either write it with or without. It's the same thing. Okay, but we do have to add near A. Okay, it's not, the statement is only in a neighborhood of A. Near A. This implies, well, we know it implies that g of x is between m and minus m. This we know. This we've been using again and again and again, right? Do you agree? But it also implies that g of x in absolute value is between m and minus m. Does everybody agree to that? Well, there's no statement in this, but if a number is less than m in absolute value, then it's clearly greater than minus m, because I can even write a 0 here. Do you agree? So this is, in fact, weaker than the statement without the absolute value. Does everybody agree to this? Wait, questions after I finish the proof. What I want to do is take this statement and multiply it throughout. This is an inequality. I'm going to multiply it. If I don't want to change the direction of the inequality, I have to multiply it by something non-negative, right? So I'm going to multiply this by f of x in absolute value. So here on this board, f of x, absolute value, times m, with a minus that was there, is less than or equal to f of x, g of x, is less than or equal to f of x in absolute value times m. So I multiplied everything by f of x in absolute value, which is non-negative. Do you agree? Everybody? Okay. Now look here. I know the assumptions of the theorem are that f of x goes to 0. Remember? We had a theorem last time that a function goes to 0 if and only if in absolute value it goes to 0. Do you agree? Remember that theorem? So we know that this thing goes to 0. Do you agree? As x goes to a. So this thing goes to 0. M is just a number. So a scalar times something that goes to 0 altogether goes to 0. As x goes to a. We just used two theorems. One, that a function goes to 0 if and only if in absolute value it goes to 0. And two, the first part of limit arithmetics. If a function goes to a limit, then a constant times the function goes to the constant times the limit. Does everybody see that we just used two theorems in writing this? Now let's go over to this side. Same thing. This goes to 0 when I multiply it by minus m. It still goes to 0. Does everybody agree to that? So I just used two theorems. Now I'm going to use... What is the second theorem? Well, one theorem is that a function goes to 0 if and only if in absolute value it goes to 0. And the other theorem is arithmetics. If this goes to 0, then m times that also goes to 0. Now I'm going to use a third theorem, which... Right, sandwich. I have here something that's trapped between two things. The two outer things share a limit, 0. That implies, by the sandwich theorem, that the something in between goes to 0, as x goes to a, by sandwich. Sandwich. Does everybody agree? Do you see that? So I just used the third theorem. Good? So I just proved that the product of the absolute values goes to 0. And now I'm going to use that theorem again, that if something in absolute value goes to 0, that's only if the something without absolute value goes to 0. I'm using the other direction of that if and only if theorem. So this implies that this goes to 0 as x goes to a, and this is what we wanted to prove. So I just proved the theorem without mentioning the definition of the limit, only using theorems we already proved. And that's fine. That's how we're going to work mostly throughout the course. We're gradually going to, we're building a large pyramid here. So the base of the pyramid is the definitions, but on the definitions we build up theorems. And as we build up theorems, they allow us to build up more theorems. That's mathematics. Yes?
What number is m?
M is the or an upper bound or a bound for G. We know that G is bounded, then we know there exists some M like this. It's an existence statement. Okay? Yes?
So when you're writing G is bounded n, you have to say smaller than or equal to that.
When I write that G is bounded, I can either write G is between m and minus m, or I can write G in absolute value is less than, we called it k previously. But we said that those two statements are if I weren't to put the equal sign here,
Yes, you have to put
no, that would still be fine. If, suppose I didn't have this less than or equal, I just had a strict inequality, but I'd have the strict inequality here. If a function lives between two things that share a limit, if it's smaller than this, then in particular it's less than or equal to that, and everything would hold just as well. It really doesn't matter. Okay, let me continue, and if you wanna argue that little point, we can do it over the break. Okay, so this is this theorem. If a function is bounded, multiplied by a function that goes to 0, the product goes to 0, even though it's more than arithmetics. So let me do a couple of examples. What do I want to erase? Okay. Yes, quick question.
Why it needs to be in the neighborhood of A?
Well, whenever we have statements about limits, they're always going to be, everything is going to be defined in a neighborhood of the point. That's what the concept of the limit can see. That's what it sees. A neighborhood of a point. In fact, a punctured neighborhood of a point. So that's always, if the function happens to be bounded on the entire line or in its entire domain, that's fine. But all you need it is to be bounded in a neighborhood of the point. That's sufficient. Okay, so examples. So example 1, let's take the function x times sine of 1 over x. Remember the function sine of 1 over x?
Yeah.
Do with your hands. How do you think of it? Right. Very good. Very good. Very good. So it's that accordion function. It's that function that wiggles and gets nastier and nastier as it gets closer to 0. Right? From both sides. Remember that function? It doesn't have a limit at 0. Right? Remember that? That was example number 5 of not having a limit. Everybody remember? So I cannot do arithmetics here. What can I do? What can I say? So what's the limit of x sine of 1 over x as x approaches 0? I can use the previous theorem. As x approaches 0, x approaches 0, duh, right? And sine of 1 over x doesn't approach anything. It doesn't have a limit, but it's bounded. It's always between -1 and 1, right? So we're in a situation where we have a bounded function multiplied by a function that goes to 0. By the previous theorem, this limit is 0. By previous theorem. What was the question?
If it needs to be bounded, if it needs to be multiplied by a function that is bounded.
Yes, that's the theorem we're using. Look at the theorem we're using. Here it is. The theorem says, if you take a function that goes to 0, multiply it by a bounded function, then the product goes to 0. That's precisely what I'm using. I'm taking a function that goes to 0, multiplying it by a bounded function, the product goes to 0. Yes?
So the neighborhood of A has to be symmetric about the x-axis for this.
Usually when we say neighborhood, we say symmetric. That's how we think of a neighborhood. That's a non-issue here. It can be non-symmetric. It doesn't really matter. But usually when we say neighborhood, we mean epsilon neighborhood. We mean A plus epsilon, A minus epsilon. And in particular, we don't care about the point itself. It's a punctured neighborhood whenever you see the definition of a limit. Okay, example number 2. Now let's take the function f of x to be x times sine of 1 over x.
Same example.
Oh, same example. Good. That's what I want. So why would I want to put the same example again?
Prove it a different way.
Prove it a different way. Very good. So, okay, we saw 2 theorems today, the Sandwich Theorem and the bounded times going to 0 theorem. We used this one, so what do I want to use now? Sandwich. Let's do it. So, do you agree that sine of 1 over x is between 1 and -1? Always. Because it's sine of something. Do you agree? So this is true for any x, in fact. Does everybody agree? Now I have to be a bit careful. I want to multiply everything out by x. I want to write that x times sine of 1 over x is also between x and -x. This is for any x different than 0. For 0, it's not defined, right? Is this true? Is this statement true? So the answer is yes, it's true, but we have to be careful. When x is positive and I multiply this by x, it's clearly true. The inequality doesn't change, right? When x is negative and I multiply everything by x, I still get it to be true, but with the negative x's. Do you see that? So I get it maybe with a less... when x is negative, I have to change the inequalities. Okay, so let's... Right, I have to change the inequality. So let's write here. For any x positive, this is true. Do you agree? For x negative, it would also be true, but with the reversed signs of the inequality. Do you agree? Yes? What happens when x goes to 0? Do you agree that this side will go to 0? I'm out of board. This side would go to 0, and this side would go to 0 when x goes to 0. Do you agree?
You need to say bigger and equal than 0.
Well, no, I don't want to say equal, because nothing is defined at 0 itself.
Oh, right.
Okay, so only x's which are not 0. So do you agree to this statement? In order to be completely kosher, if I want to do it precisely and accurately, I have to say something that we haven't defined yet, and we're going to define in a few minutes, which is, if x's are greater than 0, then what I'm doing here is going to 0 from the right, which is denoted x goes to 0, which is denoted, maybe I'll write it bigger. Let me write it here again, bigger, because it's, let me write it again. Let's do it bigger. So what we got is this. And we got this for x is positive. This goes to 0, but we're only talking about positive x's, so we're only coming from the right. And the way to denote that is x going to 0 plus. Okay? We're going to define that in a second. And likewise here, x goes to 0 plus. Do you agree to this? Yes? When x's are negative, the inequalities are going to change, and it's going to be x goes to 0 minus. X comes from the left. But in both cases, what does it imply about this? So by sandwich, look at this board a second. Look at this board a second. The picture we have here is this picture. Everything is only working from one side. Do you see that? As we go to 0, only from the right, g, f, and h are those three functions in the inequality, and we're coming, f is coming in between. So the sandwich theorem still holds. We'll write that in a minute. Okay? So by sandwich, this goes to 0 as well. This is from the right, an analogous statement from the left, therefore from both sides, and therefore the limit is 0. Do you agree? Okay, I want to define that formally. That's the next thing I want to do. Okay? So let me add that. This I can erase, because we wrote that again on the top. And similarly, the limit of x sine 1 over x is 0 when x approaches 0 from the left, and that implies that the limit as x approaches 0 is 0. So this was an introduction to one-sided limits. Let's define them formally. And then we'll sneak a peek back at that example to see that it compiles, that it fits in with what I'm going to write now. Okay, so one-sided limits. So this is a definition again. We say that the limit of f of x as x approaches a plus equals L, or as x approaches a from the right, that's another way to say this, if for any epsilon there exists a delta such that, and before I write the such that, let's make a little drawing here. What I want to capture here is exactly the picture that we had there. Here's the point A. And here's the function f, maybe something like this, f. And I want to say that the limit of f is this value L here. But f, note, is not defined to the left of A at all. Okay? F is only defined to the right of A. Do you agree? So I can only talk about something you should think of as a half neighborhood of A. I can't talk about a neighborhood of A because f is not defined to the left. So I only want to talk about a neighborhood from A to A plus delta. Do you agree? And I want to say that if x is here, then f of x is going to be in an epsilon neighborhood of A. Of L. L is still has both sides. Okay? So the statement is, instead of writing x between A minus delta and A plus delta, or x minus A is less than delta, I'm just going to write, if x belongs to A plus delta, that's saying it's in a, this is sometimes called a right neighborhood of A, implies, and this thing doesn't change at all, that f of x minus L is less than epsilon. Okay, so this is a right-sided limit. Similarly, likewise, we define the limit, the left-sided limit, when x approaches A minus. Okay, when we come from the left, when we come from numbers which are less than A. The notation is plus for the right-sided limit and minus for the left-sided limit. Okay, we're thinking of it as arriving from the minus side and arriving from the plus side. Okay, clear? Are these definitions clear?
Why, if on the x-axis it's one-sided, in the y-axis it's one-sided?
The question is why, if on the x-axis it's one-sided, on the y-axis it's both? Because this statement here, well, in this picture, this is a picture that kind of hints that maybe we're only arriving from the bottom, but that's just in this picture. There's no such statement about f, right? The function can look something like this. Okay, so it can have values greater than or less than, and that's okay. Okay, the only thing that I want is to guarantee that x's are always to the right. Okay, so the neighborhood of L is still a symmetric neighborhood. Okay, good. So, and this notion is used in several situations. The first trivial situation, so example, when we have a function whose domain is one-sided. So, for example, when we look at the function root x, we calculated the limit for this. This was one of the examples for any a greater than 0, right? For 0, we can't talk about the limit of this function because it's not defined in a neighborhood of 0. It's not defined in the negative numbers. But we can talk about the limit of this function as we approach 0 from the right. Do you agree? So the limit of root x as x approaches 0 is not defined, but as x approaches 0 plus it is defined, and what is it? 0. Is this example clear? Everybody? Another situation where we would use this notion is when we have these one-sided limits, but they're not the same. So another example would be, for example, would be the step function, the bracket, which we drew several times. So this is bracket x, the greatest integer value. Remember its graph? Everybody? At any point which is inside one of these steps, there's a limit. There's no problem, right? But if you look at one of these integers, let's zoom in on this. I made it a bit small. Let's zoom in on it. So if you look at it at an integer, that's exactly where one of these steps happens. And the phenomenon of arriving from the right and arriving from the left is very different. So let's look maybe at the step here. So here's 1. 1 is going to be our A. As you come, and by the way, the value at 1 itself is 1. So there's maybe a full bullet here and an empty bullet here to indicate that. Do you agree? The limit of bracket x as x approaches 1 does not exist. Do you agree? But if we approach from the right, it exists. And what is it? 1. And if we approach from the left, I'm approaching the same value, but from different directions, then what is the limit? 0. Does everybody agree? So this is another situation where we would be considering one-sided limits. And there's going to be a theorem. There's going to be a theorem. The limit of f of x as x approaches a exists if and only if, how does that relate to the one-sided limits?
That it's equal.
Right, both exist. Limit x approaches a plus of f exists and is equal to the limit x approaches a minus of f. Okay? So if both one-sided limits exist and they're equal, that means the limit itself exists. Okay? And if they're different, even if they both exist but they're different, then the limit does not exist. Clear?
Can we prove that?
This theorem?
Yeah.
I don't want to prove it because it takes some time. The question was, though, can we prove it? The answer is yes. I can prove it and you can prove it. But we're not going to do it in class. In order to prove this theorem, let's talk about it just a few seconds. In order to prove it, what do you need to do? You need to resort to the definitions, and there are 3 definitions involved. The definition of the limit, the definition of the right-sided limit, and the definition of the left-sided limit. You have to show that if this holds, if this definition holds, then both one-sided definitions hold, and vice versa. You have to show that if both of these hold, this holds. Okay? And it's playing around with the deltas. If this holds, you take an epsilon, you know there's a delta that guarantees f of x minus L being less than epsilon. That delta is going to work whether you take it just right-sided or left-sided. That's the easy direction. It will do this for free, for both.
What happens if we try to find the limits
by the delta and gamma and the other thing I don't remember lambda.
So what are you asking? If you want to do this and we know this,
No.
new question?
Yeah, it's a new question.
Okay, new question, yeah.
We try
Are you satisfied with my answer to the previous question?
that's
You have to try it, right? You have to sit down and try to prove this using the definitions. You're, of course, going to do that, right? Good. Next question, yeah.
If we try to find the limits on when x or fx is approaching to 1.
You're talking about this example?
Yes. that's
Okay, if we try to find the limit when x approaches 1.
Or if we say that it's equal to, let's say, 1.
Okay.
And we try to prove that with the definition of the limit.
It's not going to work.
It's not going to work.
The question was, suppose I claim that the limit of bracket x is 1 when x approaches 1, without this plus.
Yes.
And now I want to try to prove it like we did with the definition of the limit. You're not going to be able to do that. Okay? You're not going to be able to argue in any way that that for any epsilon of 1, you can find a neighborhood such that if x's are in that neighborhood, the values are always close to 1. Because whenever you take a value to the left, it's going to be 0. It's not going to be close to 1. You're going to fail. Okay? So, failing to prove a limit is true means that it's not true. Okay? Well, not exactly. Okay? The fact that you can't prove that something is true doesn't make it wrong. Okay? But one can prove that it's wrong, that it's not the limit, and that, I said last time when we discussed situations where limits don't exist, that I don't want to get into it yet, because it's just a bit harder, a bit more confusing, and this is confusing enough to prove limits that I don't want to confuse you more with proving limits do not exist in certain situations. So we argued things like that intuitively. I hope I convinced you in those examples. I don't want to do the formalism of it. Okay, it will just confuse you more than it will help. So I want to go back, now that we know what one-sided limits are, and now that we know this theorem, let's quickly go back to this second example here and see that that's what we did. Okay, so remember the example was x times sine of 1 over x. This is always true. And then we said things take kind of a fork when we want to multiply everything by x. If x is positive, we get this. Now, all this picture is true only for positive x's. For positive x's, I can take the one-sided limits. I'm only considering x's to the right of 0, positive x's. So I have this one-sided limit, it's 0. I have this one-sided limit, it's 0. By sandwich, this is 0. Then I have to take negative x's and do the same sort of argument. That was this statement. Similarly, when I come from the left, I get 0. And then, why does this imply that the limit is 0? Right. Because it equals 0 from both sides. That's that last theorem that we had. Both one-sided limits are 0, therefore the limit exists, and it's equal to that shared value, 0. Is that clear? Is what we did here clear in this example? Okay? So, one last remark, I'll write it after this theorem. Remark. All the theorems hold for one-sided limits. What do I mean by this remark? Arithmetics of limits holds. You have to phrase it correctly, okay? Everything has to be phrased with x approaches a plus. Bounded times a function that goes to 0 holds. Sandwich theorem holds. All the little theorems that we had last time, if f goes to 0, then f in absolute value goes to 0, holds. All the theorems hold. The proofs are strikingly similar. You just have to modify them very lightly to use the definition of the one-sided limit rather than the definition of the limit, and I'm not going to do that, okay? So I'm not going to even state all the theorems. I'm just going to say all the theorems that we had so far hold for one-sided limits, and we're going to use all of them freely. Question?
It's like the proof of such a theorem. Is it impossible to confirm?
This theorem?
Yeah.
What's the question?
The proof of this theorem is the possible midterm question.
Okay, so the question was, is the proof of such a theorem a possible midterm question? Answer. What exactly is asked on a midterm or on a final varies from semester to semester depending on who the teacher is. So from now on, I prefer not to address those kind of questions on video because it's not necessarily relevant to future semesters, okay? So I'll just quickly answer it for this semester, and it may or may not be relevant in the future. I am not going to ask you to prove things using the definition of the limit, okay? I do expect you to know the definition of the limit, to recognize it, to be able to understand it. I am not going to ask you to prove anything, not even examples, using the definition of the limit. Okay? We didn't practice it enough. This definition is heavy. I hope you noticed that by now. So I am not going to ask you. I do expect you to know it, and I can ask you to prove things. I'm not saying I'm not going to ask you to prove things, but not by definition. So for example, proving that theorem that we just had of bounded times goes to 0 using the Sandwich Theorem, that's a legitimate question. And other sort of exercises that start with the words prove that, based on theorems or facts that we encountered, I may ask. Let's postpone all questions related to what the midterm or the final are going to look like to the breaks. Okay? And by the way, let's have a break now and continue afterwards.
Can I